This is a short introductory video about a poster project that we're gonna present at this KAUST library session. And the title is Interpolating Wind Data Using Metropolis-Sampled Fourier Features. So there are maybe three main components here to unpack. There's interpolating wind data, there's Metropolis sampling, and there's Fourier features. So I'm going to try to explain all of these components, but we begin with a short motivation for this work. So in wind farm site planning, you typically start by looking at some sparse data of like a time series of wind measurements over a time period, and then you try to find an area that you want to further investigate in terms of if it's worth to build a wind farm there. And after you've determined a point of interest, then you would sort of go to the site, bring a bunch of tools, measure wind speeds in various areas, and then find the optimal position. But it all starts at a very coarse-grained scale with a bunch of sparse measurements from weather stations that are scattered around the geographical area that you're looking at. So in our case, it's Sweden. There are other reasons why one might maybe be interested in knowing, being able to reconstruct a wind field from a sparse set of data points. It could be like if you want to model spread of pollutants. There are a bunch of other applications. But this is the setup. So the setup is that we have access to a sparse time series of wind measurements, and we want to reconstruct the wind velocities in between these data points. So essentially what we're doing is interpolation. All right, so the data that we have access to here is a set of data points that come from the Swedish Hydrological and Meteorological Institute. And there are 171 stations to be exact that continuously measure wind speeds. And it measures horizontal wind speeds. And we also, so all of the measurements are taking over a 10-minute average, but with hourly frequency. So every hour we have access to a 10-minute average. And the coordinate system here is a projected coordinate system. I'm not going to go into details about the projection. You can find that in the corresponding article for this work. But more or less what we have is that we have an elevation coordinate, and then we have a horizontal coordinate system that we label as x, y. And since we have horizontal wind components, we're only looking at Cartesian components of the wind velocity. So one in the x direction, one in the y direction. All right, so what does it mean mathematically to construct an interpolation? Well, this could vary depending on who you ask. Some define interpolation as exactly determining to construct a function that exactly matches the measurement data in the data points, but then is an approximately close to the true function in the points where there is no data. For our purposes, we're not necessarily interested in being like matching the data exactly at the data points. We just want to have an overall good quality of fit. So we will define the notion of quality of fit later, but the basic idea is that we're imagining that we have a true function of the velocity field that goes from the geographical region, so in our case it's Sweden, to R2, like the two components of the wind field. And then the idea of an interpolation model is something that takes a set of data points in this region and then maps that onto a function that closely matches the true function. So the process of mapping that data set onto another function, that is what we call training in machine learning. So we basically want to train some model that is close to the true function. So what we want to do in this work is to investigate a very special model. So the motivation why we want to use this model is, well, there are several reasons why. But so first of all, the wind data is like it exhibits a very high variability, both in time, but also in space. So the data points close to each other are usually correlated, but if you have low wind velocities, they can be like quite different, even if you're very close in space. So you have a very high variability. It's very hard to predict wind velocities, and you have high frequency components of the wind field. Like, it's not just a sort of even homogeneous velocity in one direction. It can vary very much. And so we have to be able to capture these high frequencies. So the ansatz that we start with, the basic idea is that we start with a Fourier series, and it's a truncated Fourier series. So we just pick some frequencies. So if we were to view this from a machine learning perspective, what we would want to do is to minimize some type of loss with respect to these Fourier coefficients and the Fourier frequencies, right? So we're going to have this minimization problem that is a regularized mean square error here. So here we have the function minus the true data, and then we have some regularization term. So in our case, we're using the Sobolev norm. So like we're penalizing the first derivative and the function itself. Minimizing this in machine learning would require you to use some type of optimization scheme like stochastic gradient or something similar. The idea here is that we want to get around that, because stochastic gradient descent, it works. It sometimes tends to find the low frequency components before. So if you don't run its course completely, then you might end up with something that has more smooth properties and not as high frequency components. We want to capture those high frequency components. So the idea here, so that's the first reason why we want to use something else than just stochastic gradient descent. Another reason is that in our case, we actually want to find a Fourier series for a bounded domain. So we're going to use integer frequencies. So this optimization problem would actually be discrete in the frequencies. So you can't just naively like use some stochastic gradient descent scheme, because we have discrete frequencies. So what we do instead is that we shift perspective. So instead of having both these Fourier coefficients and Fourier frequencies being determined together by some joint optimization problem, we divide it first. So first, we want to minimize for a given frequency, want to minimize the loss with respect to the Fourier coefficients. So that is a very simple minimization problem. It's just it results in a linear system of equations that is easy to solve. Then we basically, what we do is that we sample these frequencies from some IID distribution. So each frequency is sampled according to some distribution. And the idea is then we want to optimize, we want to find the best frequency distribution. So we get this optimization here over the distribution of the frequencies. So here, these Fourier coefficients are determined using some given frequencies omega. And this expected loss here is hard to compute, but what you can do is that you can find an upper bound for this loss. And that upper bound, you can show that is minimized by picking the distribution of these Fourier coefficients proportional to the Fourier transform of the true function. That is, of course, also a problem, because we can't directly sample from this Fourier transform of the true velocity, because we don't know the true velocity. So what we do instead is that we construct a Metropolis algorithm. So this Metropolis algorithm works by iteratively updating the frequencies. So first we initialize the frequencies, and then we move all of the frequencies according to some proposal kernel. So in our case, it's just a normal, but it's a normal, and then it rounds to the nearest integer frequency. And then based off of that frequency, you calculate the new Fourier frequencies, or sorry, the Fourier coefficients. And depending on if these Fourier coefficients are more or less, like if they are higher in magnitude than the previous one, you can reject or accept it with a certain probability. And you can show that this algorithm will actually converge in distribution to the sort of true distribution that you want to sample from, if you let the number of samples and the number of Fourier frequencies tend to infinity. So it's in the limit, but it gives us an algorithm that works in the limit, which is nice. So this is the idea, and if you apply this to real world data, of course there's a bunch of optimized, like you have to do a hyper optimization over the proposal kernel and some other acceptance probabilities and all of that. But when you've done that, what you get is something that compares pretty well when you look at it sort of in contrast to well-established interpolation methods like Kriging. Kriging is more or less Gaussian process regression, right? So that is seems like an industry standard when it comes to geographical interpolation. Not that much on wind interpolation, but definitely when it comes to like mineral concentrations, when it comes to temperature, all of this, that's like the industry standard to use Kriging. So you see here is just an example of a wind field that we get, and you see that there are a bunch of, like, the wind shifts direction fairly quickly here inside of this this region, and then so the idea is then we have some training data. These are the green arrows, and then we have some test data, which are the red arrows. So if the interpolated wind field, which are the blue lines here, the ISO lines here, if that matches well with the red data, then we're good. And so this is, of course, this is just a slice of the entire wind field, but here you can see that the blue lines of the random Fourier features matches well with the test data, whereas the universal Kriging matches worse. Like the match is significantly worse. So I mean, of course, you have to care about cherry picking and so on. So what we've done is that we have also looked at aggregate measurements. So this is where the quality of fit aspect comes in. So we can look at the mean square error and the fraction of variance unexplained, and you can see that the random Fourier features is a bit better than the universal Kriging. So I mean, in general, it seems like this random Fourier features model holds up well in comparison to existing methods. And I would say that there are two main directions of research in the future, which is first this loss here that we find an upper bound to, which then results in an optimal sampling distribution. If you do this in a way that you get a tighter bound, then maybe you can get a better distribution to sample from. So that is one direction of research where you sort of try to refine this optimal distribution. Another direction of research is that you just throw away this idea of random frequencies and just try to find some type of greedy algorithm that directly works at finding the best frequencies in a deterministic sense. So there has been some work on this. I believe that Raul has been involved with this type of algorithms. But in general, I would say that this, like, finding a better bound for this expected loss has been rather untouched. So for that research direction, I would say that there's a lot more to do. So please enjoy the poster, and thank you so much for listening. If you have any questions, I will be present online during the poster session, so just hit me up with a question. I'll do my best to answer. That's it for me. Thanks so much.